Hello everyone, welcome to Illustraca. So this is the fourth lecture of this series on complete RCC building design step-by-step guide. And in this series, we are using Midas Gen 2025 software program for our analysis and design tool. Okay, so we have seen how to create this model. We have seen how to apply the gravity loads, the wall load, the flow loads, right? So today in this lecture, I will explain how you can define the, you can say, static seismic load cases, and how you can provide different parameters for the, you can say, static seismic analysis. So that we will see here, right? So before jumping into defining the different parameters in static load case, what we have to do first, we have to create a load case, right? So what I will do, I will go to load here, and if I click on this static load cases, so if you see here, we have these four cases, right? Now in Midas, you can create, you can define x and y direction both in one single case itself, right? But for our, you can say, it is always better to have separate cases for different directions, so that if you want to extract very specific data for any specific direction or also specific load case, we can directly use that particular case rather having one particular load case. Okay, so that's why what we will do, we'll be creating separate load cases for both x and y direction, right? So what I will do, I will name it as, suppose, eqx here in the name, eq sorry eqx, right? I will make the type as earthquake e, and I'll click on add. I will make another one, EQX. Now you know we have this design eccentricity. So we can have plus and minus design eccentricity, right? So for that, I will make another one, EQX plus ECC, right? For positive eccentricity. And I will make another one, minus ECC for negative eccentricity, right? So now this approach is totally on you. You can have one case and you can have both. I mean, eccentricities in different cases. So this is totally on you. So this is the approach that I prefer. You can also, I mean, have your own approach, right? Now I will change it to EQY. I will add. So this first case is without eccentricity, and other two are with the accidental and design eccentricity, right? So then it will be plus ECC, right? Add, and the another one will be minus ECC add. So you have created uh, 6 cases here. So basically this is one single case and this is one single case, but why we have created separately, so that we can have separate interpretation, right? Different cases with different I mean, we can see it differently, right? So now I will close it. So definition of the case is done, right? Now we need to apply the parameters which will through which we'll be estimating the pseudo seismic forces at different story levels, right? So for that all of us know that the seismic force or the seismic base shear is basically the product of the seismic weight of the building, okay, and the seismic coefficient. So the seismic coefficient always tells us that how much percentage of the total seismic weight is actually vibrating in that particular time period, that the static time period that we estimate, right? So for that we need to define that seismic weight. So first of all, what we will do, we will convert the overall self weight of the structure to a seismic weight, to the seismic weight, because the dead weight of the structure will be added in the seismic 800%, right? So for that I will go to structure and I will click on the structure type, and here you can see the structure type, we will select 3D. Mass control parameter, we will be selecting this lump mass, and what we will try to do, we will try to convert the self weight of the you can say structure to the seismic masses, right? So I'll just click on this convert self weight into seismic masses, right? And now in the static case we are not going to get the you can say third direction. Okay, so if you are only analyzing the structure for static case, so you can go to, I mean, you can click on this convert to x and y, but we'll be seeing the dynamic analysis part also. So for that, what I will do, while creating the mass, I will not be choosing only x and y, we will also be choosing the x, y and z. So in case we have to add any vertical vibration, okay, so in that case we can also have the participation of the z, right? So you generally you keep it this option turned on, convert to x, y and z, okay. And gravitational acceleration, so in meter per second square it is 9.806. Initial temperature, all these parameters were however it is, you can keep it by default. So we only need these two options to be turned on, and we need to select this 3D because we are performing 3D analysis. Then I'll click on OK. So what happened, uh, the self weight of the structure is now converted to, you can say, uh, uh, the seismic weight, right? So now if you remember, we have applied the self weight of the slabs also, okay, in the dead case, but it is I mean, here in the model it is not there, right? Here in the model it is not there, but we have assigned the self weight under this dead case, automatically it will be included, right? So now what I will do, I will go to load, and now I have to convert the other cases, which is my superimposed dead loads and live loads, to the seismic mass, right? So I'll go to here, and in the load, and you'll find this option called load to masses. So I'll just click on this load to masses directly, okay. So this option will be coming, right? So now we want to convert the load to mass in all three direction, x, y and z, okay. If you have any pressure load, if you want to convert that pressure load also you can do, but for us it is not there, so I'll just uncheck this. Gravitational acceleration value is there. Now see, we have already converted the self weight, okay, we have already converted the self weight to seismic mass, so there is no no need to add this particular case, this dead case, into in the additional seismic mass, okay. Even if you do, it will not be adding up the self weight in the seismic mass actually, okay. So what I will do, I will add it in this particular load case list, okay, but it will not be multiplying the self weight into 2 times, okay. So I'll just add dead. So the factor will be 1 because it is 100%. Then I will go to SIDL, factor will be 100%, right? Then I will go to floor live load and I'll make it 25% as it is less than 3 kilonewton per meter square, right? So one thing you always have to remember, that if you have a separate case for self weight, even if you are adding here in the load to masses tab, but if you are not converting the self weight into the masses in the previous option that I have shown, so it will not be actually defined in the seismic mass, okay. So here if you do or not, it will not be matter, okay, it will not be a issue. But if you are not adding up there in the structure type, then you will not be actually getting the seismic mass properly, right? So I'll just click on now okay. Okay, so you can see this seismic mass is added at every joint, correct? So now what I will do, I will go to here load, and here in the lateral panel you will find this option called seismic loads. So I'll select this seismic loads, I'll click on add, and first I will select this load case EQX. I'll select the code to IS 1893 2016. This is the latest code. Seismic zone, suppose we are designing it, the structure for maybe zone 3 or zone 4 or maybe 5. Let us say zone 3, okay. Soil type, I'll select soil type 2, medium soil. Importance factor, let us say 1. Damping ratio, obviously 5%. Now this fundamental time period for the static case, so if you refer IS 1893 part 1 2016, so there are different formulas given for bare frame, for the structures with buildings with structural walls, and then we have all other buildings. That means where when you have buildings with infill walls or any other mixed type of structural system, then you can use that I can say formulation. So either you can estimate by your own and provide the, you can say, time period here. Otherwise what you can do, you can click on this period calculator, right? And here, see, this height is already estimated from the, you can say, from the model geometry that you have defined. Okay, the D is also estimated. If you want to change this height, you can change by your own, right? But as of now, whatever height it is there, I'm just, you can say, going with the same. The formula that I will be selecting is this one: T equal to 0.09 h by square root D. Okay, so the moment I have selected this, you can see these two are active now. So automatically this dimension is, you can say, estimated by the software. Okay, even the height also estimated by the software from the model. In case you want to change it, you can change it. For y direction, as this case is EQX load case, so for y direction, whatever time period you choose, it doesn't matter because we do not require this actually, right? So I'll just click on OK. So you can see automatically the, you can say, time period is estimated. For y direction, you can keep it as it is or you can keep it 0, right? Because I am not defining for y direction. Response reduction factor, we are concerned about x direction, so both I will make it as 5. So 5 and 5, considering it as a moment resisting frame. The scale factor for x direction, I'll keep it 1. For scale factor for y direction, I will make it 0 because I do not want any force along y direction in this particular load case, correct? Now, do I need to add the eccentricity here? Now, in this case, as it is EQX, I do not want to have any eccentricity any of the directions. So I'll make it none, right? Accidental eccentricity, I do not want to add it, so just as I made it none, so you do not have to click this also, correct? So what I will do, I will click on this seismic load profile, and you can see here, so this is the story forces. Here you can see the story shear. Here you can see the overturning moment, and this is the table floor wise for the story force. Okay, so if you just click on this, so if you go to y direction, it will show you nothing because we have made it 0, right? So only for x direction this load case is applicable. Now if you click on this make seismic load calculation sheet, so it will show you detailed calculation and all the parameters that you have taken. So this directly you can put it in your, you can say, the document that you're preparing, the design document. You can put some part of this or maybe the whole page itself, right? Anyway, so once we are done with this, I will just close it and I'll click on OK, right? Similarly, we need to add for the other directions also. I'll make it EQ plus eccentricity. So I will just change these parameters to quickly, okay, for you. This for 0.09 h, correct? Sorry, I forgot to change the code. It will be 2016. Yeah. Medium soil, 5% eccentricity, period calculator. This one. Okay. Y direction, I'll make it 0. Okay. Response reduction factor will be 5. 4 direction, though I have to keep only one direction. For y direction, the factor will be 0. And here I want to add positive eccentricity, right? So I will make none for y, and I'll check this option, accidental eccentricity and inherent eccentricity. So what inherent eccentricity is nothing but the ESI. The design eccentricity, if you remember, we have static eccentricity ESI, which is the inherent eccentricity, and then we add additional 5% of the overall dimension, right? So these two are the things: accidental eccentricity and inherent eccentricity. I will show you from where this accidental eccentricity is coming, okay, in a while. So once we are done with the defining, then I will show you how it is actually being estimated. So I will check these two options, right? And now you can, I mean, similarly, you can see the seismic profile, okay? And I'll click on okay, right? Then I'll click on add EQ minus ECC, right? 2016 code. Let me just do it quickly for you. Make it 0. 5 0, and now I will make it negative eccentricity for x direction and none for y direction. Accidental eccentricity, inherent eccentricity. Click on OK. So we have done with defining the EQ x direction forces, right? Similarly, now you can define the y direction forces. If I go to EQ y, okay, I'll select. The only thing I need to change is uh, this one, this factor. Okay, so period calculator. Now I need y direction. Okay, so for x direction, anything we put, it doesn't matter actually. So y direction, this one. Okay, x direction, I'll make it 0. Here response reduction factor, I'll make it 5. Okay, x is equal to, will be 0. And now for x direction, accidental eccentricity I do not want to consider, and also I don't want to consider for y direction also, because this is the first case, right? So I'll click on OK. You can see the profile also now for y direction. For x it will be null, right? So I'll just close OK. Similarly, let me define the other two. So you can see in this particular program, software program, many of the things are automated. Okay, you can, like the time periods also, you can directly, so these two time periods, if you say 6 and 7, this is basically as per the time period formula given in IS 16700 2023. So this formula is also integrated here so that you can easily estimate the time period, right? So okay, fine, x will be 0. Now it will be positive eccentricity for y direction and none for x direction. I will add both. I'll click on OK. And I have the last one for the EQY negative eccentricity, right? So I will make it zone 3, medium soil, time period calculator. Okay. X direction, maybe I'll make it 0, 5, make it 0, and now it will be negative eccentricity, x will be none, accidental eccentricity, and inherent eccentricity. Okay, and I'll click on OK. So we are done with defining all 6 static load cases. Okay, we are done with defining all 6 static load cases, right? So now what I will do, I will close this. Now I will show you how this accidental eccentricity is estimated here. If you remember, while defining the story levels, we use this option in the control data, which is called story, under the structure tab. And if you see here, there is an option called auto generate story, through which we have estimated this. And if I go to this seismic tab here, in here, if you see, this accidental eccentricity is estimated. Now how it is estimated, we will see. Even for wind also, some eccentricity is estimated. Some eccentricity is, I think, estimated. Let me see. Yeah, if you see here, some eccentricity is estimated. Do we need eccentricity for wind? As of now, in our code, I don't think there is any such option or any such mention. So we need to modify these things, right? Even for the seismic case also, we need to see how much eccentricity, accidental eccentricity, is being estimated by the software program. So for that, what I will do, I will again click on this auto generate story data. Here, we do not want any eccentricity for the wind loading, so I'll just uncheck this option called include wind eccentricity 15%. But we do require 5% eccentricity of the planned dimension for the seismic case, which is actually the accidental eccentricity as recommended by IS 1893 part 1 2016, right? So if we make it 5%, then this 5% eccentricity will be added here in this table, and from this table it will be captured by the load case where we have checked the option for accidental eccentricity actually. So we need to see how much percentage we are giving here, right? So as per code it is 5%. So I'll just I will keep this 5% here. I'll uncheck this option and click on OK. So now this table is fine. 5% is added, and if you see the wind uh, table, you can see the eccentricity should be removed, but here it is not removed. I don't know why. For the wind, this eccentricity should not be there actually. Okay, let me do one thing. Let me first uncheck both the options and let us see. I'll make it 0. Okay, yeah, so you can see here I need to make it 0. So you can see here no eccentricity is estimated for wind and seismic. Now I'll go to auto generate data. I'll check this option 5%. You better, okay, better you make it 0, because just now we checked that if you are unchecking it and not making it 0, some eccentricity is still added here in the wind. So what I will do first, when it is checked, you can make it 0, and you can uncheck this again, and then you can check only this option, include seismic accidental eccentricity 5%, and then click on OK. So now let me see. In the seismic case, the eccentricity is added. In the wind case, there is no eccentricity, right? So this is the correct thing that we require. I'll click on close and I will save it. So this way you can define the equivalent static cases in the software program which we are using, Midas Gen 2025, right? So I hope this is clear. The whole process is clear how Midas Gen, I mean in Midas Gen you can define the static seismic cases. You can have your own approach. You have seen that in the same load case we can define both the directions. This is also possible. So you just have to create for positive and negative eccentricity. I mean 3 cases only, where you will have both x and y with positive negative eccentricity and without eccentricity, both cases, right? So that you can do as per your requirement or as per your practice, right? So let me know if you have any doubt in this particular thing, defining the static cases, right? Now one more thing I want to show you. I think I have missed it. So in the control data, in the same option, if I go to story, so if you see here, by default we have considered you can say rigid diaphragm here in the story level, right? So it is saying flow diaphragm, consider, 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 and consider. Now the problem is this 1F level is nothing but the base. In the second floor level there is no slab or there is no floor system, right? It is only beams. So in the second floor level we have to consider that there is no diaphragm. So all the, I mean there is no in plane element which will transfer the force from one end to other end. So all the forces will be transferred through the beams, right? From one column to another column, right? One joint to another joint. So in this case we should not consider any diaphragm at the this level, this plinth level, because there is no slab, right? Though there will be grade slab and all, but it is always recommended not to consider, because the grade slab will not be integrated with the beams and all, right? So because it will be suspended on the you can say the filled up soil itself. So what I will do, I will change this from consider to do not consider, only for 2F level. 2F is nothing but this plinth level, right? For rest of the levels we will have this you can say static I mean rigid diaphragm defined, right? So through this we can only define rigid diaphragm, okay? For defining the how to define the, you can say, flexible diaphragm, that we will discuss in our upcoming lectures, right? So once we are done with this, then we are done with this particular tab. We don't have to do anything else here, and we can close it, right? So now we have defined the you can say static load cases. We have defined the other cases also. So just to show you how whether it is working or not, what I will do, I will go to analysis here and I will directly perform analysis, right? We will discuss about this analysis again in our upcoming lectures, but for now, just to show you the deformed shapes corresponding to the different lateral load cases that we have defined, I'll click on this perform analysis. I will just wait for a few seconds. You can see it is running the analysis. So the solution is done. Okay. Now I will go to results here, the results tab. I'll go to deformation and I'll click on this. Suppose displacement contour. I want to see the contour also, right? Now I will select here EQX, right? Let me go to the top view so that we can easily see here. First I'll click on DX because we want to see the displacement along X for this particular case, right? I'll click on apply and now it is only showing contour, right? If you want to see the deformation shape, so you click on this deform. I also see the legend, so I'll click on this legend, right? And I'll click on apply. you can see it is showing you the deformation shape. If you want to change the scale, you can right click on this three dot beside the deform, and you can change this scale factor to suppose say 4 times, and I'll click on OK. So you can see the deformation shape in the plan, right? Now if I change it to eccentricity, so if you see, you will see a torsional effect. So you can see here. Okay, now here why it is behaving like this, because we already have some inherent torsion here. By seeing this deformation shape, you can see this particular portion is moving less, this particular portion is moving, I mean displacing higher, because here we have this rigid portion by the shear walls, right? So this is EQX. So with the eccentricity, additional eccentricity, it is almost becoming I mean it is reducing. Actually the eccentricity is reducing, and if I go to minus eccentricity, it is different now again. So that's why it is always better to have three cases. Okay, so you can see EQY, EQY ECC, and EQY minus ECC, right? So it's not affecting EQY much, but it is affecting the EQX, right? So if I just go to my isometric view, let us go to EQY again, right? Okay, sorry, I my mistake, I have selected dx here. For EQY it will be dy. Yeah, now it is correctly visible. Sorry, let me see the top view. EQY plus eccentricity, EQY minus eccentricity, right? Fine. So EQ, let me show you in the 3D view. EQX for dx, sorry, and EQY for dy, right? If you want to see the animation, so you can click on this animate, you can click on apply, and you can click on this record button. It will show you the animation also. You can correctly understand whether the load that you have applied, it is in the correct direction or not, right? If I change it to EQX and DX, apply and record again, so it will show you the deformation shape, right? So that means we can understand that the load that we have applied is in the correct direction. And if you want to estimate, I mean if you want to see the base shear that is being estimated by the software, whether it is correct or not, you can directly go to this load. I can let me close it. You can directly go to this load, and you can go to the seismic loads. You can click any of these, modify, and you can click on this seismic load profile. Okay, from here itself you can see these values, or you can go this calculation sheet. Okay, and you can have a look on this, what is the base shear estimated by the program, right? So I hope you have got a clear idea about how you can actually analyze your structure for static seismic load, right? Obviously for the analysis part we will be discussing later, but it's just to show you that the load is acting properly or not. Okay, I have analyzed the structure. So if you have any doubt in this, you can always write me in the chat box, in the comment, or those who have already joined my the group or the WhatsApp group dedicated to this particular series, so we can discuss over there as well. If you have not joined the group yet, the link for the WhatsApp group is given in the description. You can always click on that link and try to join the WhatsApp group, okay, where we discuss about the application, the technical things about this particular series that I'm making, especially, right? So this is it for today. If you like to see more such videos, and if you have any suggestion to, I mean to add, so please write in the comment so that we can look have a look on this, and we'll try to we can say make lectures on those. Thank you, and we'll see you in the next lecture.